Okay, good morning, everybody. We will start. So welcome to the first of a series of 3 webinars that we are organizing in the frame of the NuReDrain project. My name is Charlotte Boeckhaert. I am the project coordinator and I will be your moderator for today. Let me first start with some practical arrangements. So I want to ask to everybody to mute yourself, and everybody is doing so that's perfect. So during the presentations, you are free to ask questions in the chat. I will make sure I follow up these questions, and after each presentation, we will do a Q&A, and then I will ask some questions to the presenters. In case there are more questions than there is time, then we will make sure that the questions are answered by written means, so you will get a reply by the presenters. Also for you to know that this webinar will be recorded because some people could not attend and asked if it could be put available afterwards. And we will also give you handouts once this presentation is finished. Okay, so before I give the floor to the presenters, I first want to briefly introduce you to the NuReDrain project itself. So NuReDrain stands for Nutrient Removal and Recovery from Drainage Water. Our project will last for 1 more year, and it's a project which is funded by the Interreg North Sea Region program. We are with 11 partners cooperating from 3 different countries, being Denmark, Germany, and Belgium. So the goal of our project is to combat eutrophication by installing end-of-pipe technologies to remove nitrogen and phosphorus from agricultural-related waters before they enter the surface water. And our project goals is to develop filter technologies that can remove at least 50% of nitrogen, 70% of phosphorus, and with the phosphorus that is being retained, we aim to reuse at least 20% of it as fertilizer. And we would like that our technologies can be adopted by at least 40 organizations at the end of our projects. So we focus on drainage water, but we also consider greenhouse effluents. We also have a field case on in-ditch technology to treat the surface water directly. And we also have a case in which the water in a water reservoir is being treated before it is handled for drinking water production. We have 6 field cases in the project spread over the 3 different countries, and today we will focus on the results of 3 of them, and today we will handle the removal of phosphates from drainage water. So, and with that, I would like to give the floor to Christine Bolte. She's from the Chamber of Agriculture of Lower Saxony in Germany. So, Christine, please take control, and the floor is yours.
So thank you, Charlotte, for the introduction. Good morning, everybody. I hope everybody can see the images. I'd like to present you the results from the 2nd drainage season of our phosphorus filtration in drained arable fields here in Germany. Next slide. So just to give you an impression, we are located in Germany. In the upper right image, you can see the picture of Germany. In red, it is the federal county of Lower Saxony, where our field site is situated, indicated by the small blue dot in the very southwest. On the map, you can see that our target water is the Lake Dümmer. The catchment area is circled with a red line. green areas are indicated as being high, endangered by high drainage losses. And our test site is circled in blue. The aerial image gives you an impression about the soil types in that region. You can see that they are dominated in the western part by organic soils and mineralic soils high in organic substance. Our test site is in the transition zone between organic to mineralic substances and indicated by the red circle. Our field size is 8.2 hectares in the transition between peat soils and mineralic soils. It is a loamy sand with a very high percentage of organic substance in the topsoil. It's drained by single tile drains in an average distance of 8 to 10 meters, and we can expect P values for P total about 4.0 milligram per liter. And for P soluble, it is about 0.3 milligram per liter. The LBEG has examined this site for many years, and these are the values expected. Oh, Charlotte, the presentation is gone. It's gone. Charlotte? The presentation is gone.
Yes, sorry, I heard your thing. Sorry, I was answering in the chat. I should stay out of the chat. Sorry, let me fix it. It's here. Sorry, I need to reshare my screen. Sorry, people. Okay, I will just, yeah. Okay, go ahead. Yep. You will take over or?
Yes, I will take over.
Okay, go ahead. In the meantime, for people who could not see the slides in the beginning, I hope it's solved now. In case you would not see them yet, then you need to go out of the meeting and join back again. And normally it's solved then. Okay, sorry, Christine, go ahead.
Yes, so our site, the special thing about our site is a very high percentage of organic material in the topsoil. And there can be a very high discharge of amorphous organic substance into the drainage water. This is a setup of our P filter. So the original drainage pipe is cut. It ends in an empty vessel. This is a pre-filter. The pre-filter removes organic and mineralic substance from the drainage water to prevent the clogging of our P-filter. Then the cleared water is transferred into another vessel. This is our P-filter. It is filled with iron-coated sand from the drinking water production. We sieve the material to an average grain size larger than 3.15 millimeter in grain diameter. After passing the P filter, the water is discharged into the receiving surface water. We are automatically measuring the flow in the transition between pre-filter and P filter. This is indicated by the gray dot. The red dot is the extraction of unfiltered drainage water samples. The green dot is the extraction of filtered drainage samples. We are continuously measuring, or more or less continuously, 10 samples per day are extracted automatically.
I'm sorry, Christine, to interrupt. Perhaps it's my fault, but I don't see that slide yet. I just want to double check. It's the first time we do this kind of webinar. I just see the slide high P losses in drained fields. I don't know if that's the case for the others also.
Well, the slide should be set up P filter.
Yeah, I see the correct slide.
Okay,
yeah,
go ahead.
Me too. I also had a problem, and I went out of Teams and joined with the online, let's say, without the Teams thing, and it worked.
Okay, perfect. Yeah, thank you.
Okay, I go on. These are the preliminary results for drainage water sample analysis. Without filter, we can expect minimum values for P total between 0.04 and 3.07 milligram per liter. For P soluble, the values range between 0.01 milligram per liter and 0.08 milligram per liter. So the values measured are clearly below the expected values, but they are clearly exceeding ecological targets. So there is a range of ecological targets. For example, in Germany, it is a surface water ordinance, which says values should be between 0.1 and 0.3 milligram per liter. But there are also other values, like, for example, 0.03 milligram per liter as a target value for algae growth. If we put a filter to this system, the P total values range between 0.04 and 3.19 milligram per liter. For P soluble, values are only varying between 0.01 and 0.02 milligram per liter. So if you compare the maximum discharge for P total, you can unfortunately see that the highest discharge comes from the filter. This forced us to revise our sampling method. Values for the flow balanced nutrient discharge for P total on the left side and P soluble on the right side indicate that. Unfilled symbols are for the filtered water samples, and black symbols, gray symbols, are for the unfiltered sample. So you can clearly see before filter revision, the filtered sample has higher P total values than the unfiltered one. After revision of the sampling mode and the filter setup, P total is retained, and we see a clear reduction of P total by the filter. If we look about the discharge of P soluble, we can see P soluble is retained, but it's not a significant reduction. The percentage of P soluble compared to P total is only 7%. That means the total P discharge is mainly determined by particulate P in our filter site. These are preliminary results from flow rate, retention of P total, and retention of P soluble. The blue line shows the flow rate. As expected, flow rate is varying between 0 cubic meter per day and a maximum of 22 cubic meter per day. The green line is a retention of P soluble. It indicates how much P is retained in the filter. You can see that it is nearly not varying at all and does not seem to be influenced by the flow rate at all. The retention of P total is indicated by the orange line, and you can see a strong negative retention, which means that the P filter is emitting phosphorus. After revision of sampling mode and position of the sample extraction, we see a positive retention for P total. That means P is retained in the filter as it should be. You can also see that there is no strong correlation of the discharge and the flow rate. There's often a change in reaction time between the effect and the cause. It's called the hysteresis effect. If we extrapolate the P loss per season and hectare, we can see that with no filter, it's a red bar, we have a discharge of nearly 800 grams per hectare and drainage season. If we put a filter to this system, we can reduce this outflow of P total by 83%. That means 83% of the discharge are retained in the filter, and the total discharge with this filter implied is only about 140 grams per hectare. there is no clear reduction of P-soluble, so it's not retained in our system. If we assume that under realistic conditions, 1 gram of P promotes the growth of 330 grams of phytoplankton, we can state that by putting a filter onto our system, we can save 230 kilogram of algae growth per season. To explain this graph, if we do not have a filter, it is as much P emitted as the growth of 250 kilograms of algae needs. So by putting a filter to our system, we can prevent the growth of algae. If we cross-check our results, highlighted in pink with results from literature, we can state, compared to Ulen et al., that we have a 2.5-fold higher discharge than they. We can state that also on our side, the main P form is particulate P. They stated that a large amount of the phosphorus discharge can happen within short time intervals, and we can confirm that. But we do need more data to do any precise statements. McGrath et al. Found out that the tile chart discharge is highly variable within events. We can confirm that too. Zimmer et al. Stated that the amorphous organic substance is a carrier of P and can cause a high P input into surface water. This would help us to explain large differences between the results from season 2, which I presented to you, and the results from season 1, which I did not show because there were nearly all results very close to the detection limit. So nearly no P discharge took place in season 1, and we did not observe the discharge of amorphous organic substance in season 1 as well. Schaden et al. Promote ICS as a good material for field use due to its high hydraulic conductivity. And we have to confirm that due to the low hydraulic gradients in open field agriculture, it is very important to have an eye on the hydraulic conductivity of the material. The ICS filter efficiency in investigations of under NuReDrain project partners is above 80%, and we are very, very happy to confirm that. So if we would like to transfer our setup into practice, it could be built in as a new installation or as an extension of existing collector drainage systems. So a collector drainage system has several single drainage tiles, which are combined in a collector shaft and then normally discharged into the receiving surface water. If we take this collector shaft as a pre-filter to prevent clogging, we just need to install a second shaft filled with the ICS material, which then acts as a P-filter, and then the water is discharged. What are the benefits of such an installation? The ICS material is a very cheap filter material, only about transport cost. It is a low space consumption because it is installed underground. No energy supply is necessary. It is renewable in own work, and it has a long-term filter effect compared to drainage tile sheeting and drainage tile bedding because it is renewable. If the filter material is saturated, you can lift it up mechanically if you quit the manhole cover and exchange it for a new material or even other material. So future perspectives within NuReDrain. We want to have a good last measuring season. That means avoid data loss by poor measuring conditions, by damage or malfunction, and avoid erratic measurements by backwater clogging or preferential flow, to expand our database and to make a statement about the long-term filter performance, to improve our filter and to put it into practice. But before putting it into practice, we should ask more precisely for the farmer's needs and wishes, which is also about money, as always, and legal requirements. Develop a cooperation, which is not only the willingness to cooperate, but also the practical implementation. And then we have a pretty follow-up project from NuReDrain with an improved starting point. This is thanks to all the other project partners delivering their results and experiences. And yes, I'll be happy to answer your questions. Thank you.
Okay, Christine, thank you. I can see that people still have some troubles to get access to the slides. Some people join and then leave again. So I have not noted any questions in the chat. I'm just wondering to the people who are present, are there any questions? If so, you can temporarily unmute yourself and just ask your question directly to Christine. No, yeah, Bernd, you have a question?
So my name is Chris Daze.
Ah, okay, yeah.
Christine, I wanted to ask, I missed the specifications of the phosphor pre-filter. What is it more specific?
Yes. The pre-filter, in our case, is just an empty vessel with a volume of approximately 750 liters. So the drainage pipe ends in this pre-filter. And by this increase of volume, you have a reduction of flow velocity, which allows organic and mineralic material in the drainage water to settle down in this pre-filter. So the organic material in most cases is floating up, or it is connected to the walls of the pre-filter. We do not have that much issues with mineralic substance. And from the pre-filter to the P-filter, there's an additional mesh netting. So we take the water from the middle water body of the pre-filter and transfer it into the P-filter to get rid of the organic substance. This is the main problem in our field experiment.
Okay, nice, thank you.
You're welcome.
Okay, then Bernd Lennartz has a hand shown. I don't know, Bernd, do you have a question? Or is it by accident that you touched your hand? There's no reaction. I think it's per accident. In the meanwhile, Christine, I got another question. The question is, do you have experience of filters that are already saturated with P?
Yes, no, not directly. Our filter is not yet saturated, but other project partners have already saturated material, and they are doing experiments with the removal of phosphorus from this material, or the direct use of saturated material in plant testing, if the plant has any benefits from the saturated material. Charlotte, I'm sure that this topic will be followed up in another session, right?
In the next webinar, we will cover this, but so in case that the filter material is saturated, then it's taken out of the filter and it's renewed with fresh material. That's how we work. A follow-up question also was, if the drains are below the groundwater level, do you already had problems with anaerobic conditions?
Yes, the drainage tiles are ending below the water level, as you can see on the photo right now on the slide. And it's under pressure, so suction drainage. We do not have that much problem with anoxic conditions, or we didn't measure it up to now, so I cannot clearly answer this question.
Okay, then I see that Bernd has problems to unmute himself. He asked if I can unmute him, but I don't think so. Perhaps I can, but I'm a bit afraid to touch the wrong buttons. So Bernd, you just need to unmute yourself. You see different icons, and the one next to the camera is to mute or unmute yourself. So try it, and then you can ask your question. Or type your question, can also be.
Charlotte?
Yeah.
I don't know, but maybe I can add on the saturations of the P grains. Yeah, it seems that the P grains, certainly the ICS grains, can hold more P than expected. So we did a lab test, or the KU Leuven did lab test, and there they had a saturation of, for instance, 5 milligrams. And we see in the field that it's lots of more. So it can go to 16, even 20 milligrams. And that's because the water is not continuously going over the grains, but discontinuously. And that has a very good effect on the capacity of the P grains. That's maybe some extra information on the question about the saturation of the grains of the filters.
Okay, then, yeah, sorry, Bernd, I tried to unmute, but I can't. It's hidden. Christine, the question of Bernd is, what can you say about the dimension of the filter in relation to the field site?
Yes, to treat the total drainage discharge from our field, it should be 11 times larger because there are 11 single tile drain endings in this 8.2 hectare sized field. So it will probably not be a solution that could be transferred into practice to put such a filter device in every single tile drain ending. So it's a test site, and it works well for the discharge of this tile drain. But if we put it into practice and treat a larger volume of drainage water, we should increase the volume of the filter site as well. I think so.
And what is the volume now? I mean, like just the size of the filter? Like you said, the pre-filter.
Yes, okay. So the diameter of the P filter itself is 1 meter. So 1 meter concrete elements. And the filter dimension is 40 centimeters filling height of the material. And yes, over a distance of 1 meter needs to be flown through by the drainage water before it discharges into the drainage tile and then into the surface water.
Yeah, okay. Then more questions are popping up. Do you sieve the material to have a better hydraulic conductivity?
Yes, the ICS material was sieved to remove this sludge particles between grains and to achieve a better hydraulic conductivity, because as you can see on the photo, the driving hydraulic force is very, very low.
Yeah, okay. I will just take 2 more questions, and if other questions remain for Christine, I will just note them and then you will get your reply directly by Christine. The question is, do you have any idea about the differences in composition and adsorption capacity between various batches of ICS?
I do not have a precise idea, but I know it was investigated by project partners in the lab.
Yeah,
so they are the ones to answer this question best.
Yeah, and I think Yeah, to Leonard to already answer that question. Of course, ICS that we are using is derived from different drinking water companies, so there can be a slight difference, of course, between the ICS. But in general, the absorption capacity is quite good, very good actually. But the colleagues from KU Leuven are working on that, and I think if you really want to know more, they are drafting a scientific paper on it. So for sure, we can share that information. Okay, and then the last question for you, Christine, is you do not seem to use pumps within your filter system.
No.
So does it mean that your drainage flow rate is high enough?
The hydraulic gradient is high enough to let the water flow through the filter, but the filter material itself causes was heißt Rückstau? Was heißt Rückstau? It causes a, oh, Charlotte, what's the word for it?
Backflow? I don't know.
Yes, it causes a backflow, so it hinders the free water flow. If you put anything into the drainage tile, it is an obstacle. So it causes a backflow of water in the drainage system, but it is more or less flown through. We do not have overflow. We do not have preferential flow. But if I could wish for something, it would be a larger gradient. A larger gradient. If we use even coarser material, then water is passed through the filter so quickly that there is a very low retention time. It's a very site-specific decision how coarse or how fine can the material be. The coarser, the higher is the hydraulic conductivity, but the lower is the contact time. So you have to figure it out. What are the site-specific conditions and what is the most important thing, and then follow one by one.
Okay, yeah. We'll leave it here for the time being. Thank you, Christine, for your presentation. And then we now move on to Lorenzo from August University. So Lorenzo, can you please take control?
Yes. Good morning, everyone. My name is Lorenzo Pugliese, and I'm a researcher at Aarhus University. Yes, I'm a researcher at Aarhus University. Today, I will present our filter system and for pee removal and its results. Before doing this, I would like to give you an idea of the problem scale. So the figure and the graph to the left of the slide show the results from a research study on Danish estuaries and coastal waters. All these areas were markedly affected by eutrophication during the 20th century. Therefore, the government since 1985 started implementing some mitigation measures, and this has resulted in a great reduction of the point sources, which you can see in the graph. And this reduction was up to 90%. However, there was no big effect on the diffuse sources. Thus, there was a problem to be solved. An up-to-date risk map is shown instead to the right. It's from 2020, and it calculates the transport, macropore transport, macropore transport to drains. This is generally related to soil texture and climate. We can see that These catchments with high losses are primarily located in the East Ulan, which is characterized by moraine soil, and also in Zeeland, which is the southern eastern part of the country. However, there it's slightly lower because of the lower amount of precipitation. In one, somehow my precipitation, I'm not really controlling my. Another user took control of my presentation apparently.
I did not take control, Lorenzo. I don't know, Christine, did you touch something?
Okay, I'm trying to.
I did not do anything.
Okay.
Okay, now it seems that I have again control. Yes, so we were still at this slide. Yes. Okay, this slide shows our catchment area, which is delimited by the red line. This area has been monitored for a couple of years, and we can see in the graphs the variation of the drainage flow in time on the top graph, and also the variation of total phosphorus concentration across these two hydrological years. The catchment area is an extension of 8.4 hectares, and the table reports some key parameters like precipitation value and the ratio QP and total P in kilogram per hectare, and the flow weighted average total P. Yes. This is a schematic of our filter system. It was constructed in the beginning of 2019 under the NuReDrain project. It is constituted of 6 cylindric wells made of concrete. So you can see here the drainage inflow enters first well 1, which is housing an electromagnetic flow meters, which is needed to measure the incoming flow. Afterwards, the water moves to well 2, which is a distributor well. This well is also equipped with a valve, which can be used to regulate the hydraulic load to the system, and it's also equipped with an overflow to be used in case of extreme runoff events. From tank 2, from the well 2, the water moves to well number 3, where the sediment filter is located. This is a 2 meter diameter well, and the main purpose is to remove the sediments and those particulate bound phosphorus. From there, the water enters then the reactive filter, which contains the reactive P filter, reactive material, and finally moves to the outflow, to the well 5. As you can see in the picture, there is an additional well, which is the number 6, which we call the sludge tank. There we gather the sediments, which are from time to time collected from the sediment filter, and they are pumped in the sludge tank for improving the thickness of the sediments. Yes, this is a picture of our sediment filter. So the sediment filter is one of the main components of our system. So as you can see in this photo, water enters from the left. So the sediment filter is divided in two chambers. So the water enters from the left. You can see this orange pipe. It moves first downwards, then it moves upwards to this filter with a bigger mesh, and then it moves to the second part, to the second chamber, and moves downwards. From the bottom, then it moves upwards to this the pipe which leads the water to the following well. This well is also equipped with a bypass for facilitating cleaning operation. And on the top, you can see a system for flushing this filters. So from time to time, we automatically flush the filter to remove the sediments which are trapped into the two different small filters here. There is a small video which somehow, yeah, let's see if I can. I somehow cannot press the button to start the video. Charlotte, could you help with that? If I just, because it's covered, the button basically.
I also don't see really a button to start it. Otherwise, I need to go in your original presentation. But sorry, now the presentation is gone. Wait. Do you still have the presentation in front?
No, I can't see the.
Wait.
Yes, it's loading now.
You will. I'm going now to the video. I think
yes,
it's here.
It's the one before. Yes.
Yeah. And then wait. Let's hope I. Oh.
Okay, maybe we can leave it.
Yeah, I would leave it. Sorry.
Okay, I take control now.
Yeah.
Yes, this slide shows the other main component of our system, which is the reactive filter. So the reactive filter is basically a cage constituted of two cylinders, and this cage has an height of 2 meters, and the cylinders have a diameter of 0.8 and 1.5 meters. As you can see in the cross-sectional view to the right, water enters from the left and then moves radially toward the inner part of the filter. And then it's collected at the bottom, and through a pipe, it reaches the outflow. So the filter materials we are using here for treating the drainage water is Diapure, which is produced by one of our project partner, and you can see here it's has this red color because the grains are coated with iron, and you can see on the top picture. To avoid problems with potential problems with overflow during extreme runoff events, we have topped the Diapure with some seashells, which you can see in the lower picture. And yes, so the water samples were taken by some ISCO samplers, and this is done automatically. So the ISCO sampler takes 30 milliliters of water each hour and puts them together into 1 liter bottle for an entire day. So every 3 weeks, then one of our technicians went out to the field to pick up the bottles, which were brought to the lab and analyzed for pH, electrical conductivity, TP, total phosphorus, and dissolved reactive phosphorus, and turbidity. In total, we used 3 ISCO samplers. One was located at the inflow, one was located between the sediment filter and the reactive filter, and one was located at the outflow. Yes. Here are the results for total phosphorus. So the graph shows total phosphorus in milligram per liter over a selected period of time, while on the secondary y-axis we have the drainage flow in liter per second. So if we want to see here the overall effect of the filter, the system filter, in terms of total phosphorus, we should look at the results for ISCO in and ISCO out, so the green and the blue line. So we can see that at the beginning there is a good removal effect, but this removal effect later on drops. If we want to see what is the response of the sediment filter, we need to look at the results from ISCO in and ISCO set, so the green and the red line. We can see actually that there is the red line is often above the green line. This indicates that actually it's the filter is releasing phosphorus instead of removing it, and this indicates that some sediments actually are not well trapped by our sediment filter. Overall, we can see a breaking point around the 18th of October. And after that breaking point, there is no a clear removal effect based on these results. This graph shows the dissolved reactive phosphorus in milligram per liter during the same period of time. Here, if we again look at the overall effect in terms of TDP removal, we can see that initially the system was removing it, while later on this removal effect dropped. And if we want to look a bit more closer to the effect of the sediment filter, so we need to look at the green and red line. We see that actually they almost overlap entirely, and this is how it should be, because the sediment filter is supposed to decrease particulate bound P, not influence the TDP concentration. Also here it can be identified as breaking point around the 18th of October, and after that time actually there is almost no effect in TDP removal. And here are the results for the turbidity, so measuring NTU over the same time period. So we can see, first of all, that highest turbidity during intense runoff events. So during high peak coup, and yeah, in the first part, overall we have an effect also here in the first part of the monitored period, which later drops. And at the beginning, there is no effect from the sediment filter. So if we compare the data from the red line and the green line, so this shows that the sediment filter is not capable of retaining the sediments which are brought into the system by the drainage. And yeah, after also here, there is the breaking point. So after this 18th of October, there is no remarkable difference between the three lines, the data from the three different ISCO samplers. Here is a summary table, which shows the average removal in percentage for different time periods. So I divided here the time period from the start until the breaking point, which was the 18th of October, and then the following time period. Additionally, I reported the data from the entire month of February 2020. So if we look at the drainage flow, we can see that in the first period up to the 18th of October, we had the lowest Q, which was 1,400 cubic meters approximately. This volume doubled in the following period and was the highest in February 2020. So again, looking at the overall effect of the filter, so we need to focus on the results in the middle of the table. So where is written ISCO in, ISCO out. You can see in the first period quite good removal, average removal in percentage, which drops drastically in the following period. And this trend is also confirmed later on in February, when we had very high Q. To the left, to the right of the table, we see the results which show the effectiveness of the reactive filter. So this data are calculated by using the data from the ISCO set and the ISCO out. So we can see that initially the reactive filter worked pretty well, and this removal capacity later dropped. And it dropped because the sediments were not taken by the sediment filter and clogged partially the reactive filter. This reduced the absorption capacity of the filter itself. And this trend is reflected also in the data we obtained for the month of February. So based on the data I have shown, in terms of future perspectives, I can say that with our filter system, we have some challenges, and the main challenge is actually has been the retention of the sediments. There are, of course, other small challenges, including, for example, the replacement of the reactive filter material, which appears to be clogged, so and less effective. So as possible improvements, we are looking at alternative physical methods for removing the sediments, or alternative chemical methods, which include flocculation with aluminum or iron. Yes. Thank you for your attention. So if you have any question, I would be very, very happy to answer.
Okay, thank you, Lorenzo. It's nice to do field tests because this brings you to the reality and makes it challenging, of course, to find new solutions. Does anybody has a question for Lorenzo? I have two questions. I will start with the question of Maria. She asks, so you have your sediment, what is the problem? Are it particles, soil particles? Is it organic matter?
Yeah, it's very small particles, which are basically cannot be retained by the sediment filter. So we have run some lab analysis also to see what kind of particles. So it's basically colloids, so it's very small, and So that's why among the possible solution, we are also looking at flocculation.
Okay. Chris, you also have a question. Please go ahead.
Yes, indeed. Lorenzo, wouldn't it be a solution to install a backwash system in the reactive phosphor filter to remove the sediments? Now, yeah, you just told it are small particles. Maybe that's okay. It will be hard also with a backwash system, but yeah, still, I ask you.
Yeah, we have thought about the backwash a few times, but due to the size of our system, as you could see in the slide of the schematic where we're showing the system itself, due to the size of it and the accessibility, I think it's a bit too complicated. So we really had good hope that with this extra sludge tank, we would extract from time to time the sediments and avoid the clogging of the entire system, but that was not sufficient. So we are actually looking at better solution for the sediment filter, not for the reactive filter itself, because we believe that the problem is in there.
Yeah. Okay. Thank you.
Thank you.
Okay. Are there any more questions for Lorenzo? In the meantime, I will prepare the slides for Roy. Does somebody else has a question? Okay, Roy. Thank you, Lorenzo. Then I think we can give the control to Roy. If it's working for you, Roy.
I'm trying.
Okay, go ahead. If not, I will just move on your slides. Huh?
I think it should work. Good morning, everyone. My name is Hui Xu. I'm a researcher from Department of Environment at Ghent University. Very glad to see the results from our project partner, how this filter works in Germany and Denmark. Now I will talk about the application of iron coal descent filters in Belgian agricultural fields. Let's start with why the filter is important. In Northwest Europe, agricultural diffuse phosphate losses is a major cause of nutrification problems in surface water. Since last century, intensive fertilization resulted in the increased P in soil and high P saturation degrees. If we look at the map, we see high to very high soil P value, blue to dark color in Belgium, the Netherlands, Denmark, and part of Germany. And when it rains, P is discharged directly towards the surrounding water over the land via the shallow and deep soil layers. In Northwest Europe, 70 to 40% of agricultural field is drained. With the drainage system, rainwater flows via the drains, and we have one concentrated source of nutrient supply into the stream, where could be tackled with a filter. Therefore, the filter could be a potential solution to reduce phosphor loads. To develop such a filter, what do farmers need? Of course, they want a filter have very high P removal efficiency to reduce the P loads as much as possible, at least smaller than 0.1 ppm to meet the standard from Water Framework Directive. It should be also be able to handle water flow of 6 to 8 cubic meter per day for individual drainage pipe. During the on and off season to process this continuous flow, very important, is to keep low cost and easy installation. For the P filter development, I will cover in the coming slides with P sorption materials and principle, lab and field scale evaluation, development and performance for prototype. P sorping material showing the best P removal are often rich in iron, aluminum, calcium content with large specific surface area. For example, iron-coated sand, which has been mentioned previously, it is a byproduct from drinking water industry, and glauconite that is naturally available minerals. After checking mineral composition of different material and taking into account of environmental risk and P sorping capacity, iron-coated sand and glauconite were selected as potential filter material because they cause no other contaminations. If you are interested in other materials that we evaluated, please check the paper published by my colleague in water research. Principle of P removal is quite simple. I will take iron-coated sand as an example. Iron-rich filter materials dissolve reactive P phosphate, more specifically by exchange with hydroxyl to reduce P from water, as shown on the right side. At lab, we evaluated the filter material characteristics, such as saturated hydraulic conductivity, how fast water can move through the filter, and we look for the high value because the space for P removal is limited in the filter. We also tested P removal efficiency, of course. Fast P absorption is important. This graph shows how the simulation experiment was carried out in the lab. Phosphate was pumped out from the supply vessel to the buffer vessel, then went through the filter. In this way, hydraulic conductivity and P sorption capacity could be tested. As a detail of the evaluation, you can also check in the paper. In the end, iron-coated sand was assessed to be the best, allowing the peak volume to be processed, meanwhile sufficient reaction time to be kept. Next step, and together with our colleagues from INAHRO, we carried out field experiment to check the P remove filter performance in the field. We evaluated the filter in 3 different experimental sites in Belgium: Zelderhem, Staten, and Enzerhem. There are 3 individual drains in Zelderhem, as you see in the photo, with maximum water flow 8 cubic meter per day. We will focus on this site because the water from Staten and Enzerhem was drained for a larger field of 1 to 2 hectares, which was beyond the capability of the designed filter processing. Okay. Here is a design idea for the bucket filter. Is that water enters the filter and has reaction with the filter materials, afterwards goes out. A few important features: there is a mesh netting at the bottom, stop the big particles, and upward oriented outlet, let the sediment, possibly particular P, stay at the bottom. The overflow could go directly to the right when the peak flow is higher than the capability of filter processing. With this principle, we have designed several different generations of the filter. Here are 2 of them installed in the field. We designed the prototype with similar principle. It is installed at the end of the individual drainage pipe. Water enters from the left and goes right at the bottom. Then it has a reaction with filter material and goes out to the ditch. 2 important features were kept: upward oriented outlet and mesh netting at the bottom and top to stop the sediment. The photo shows the prototype installed in the field. So let's look at the performance of prototype in the field. We used iron co-descent as a filter material and compared simple bucket filter and prototype filter in the field. Here, total P and dissolved reactive P presented in yellow and blue bars. Inlet and outlet P concentration are in dark and light color. The water flow shows below the graph was similar. On average, 84% of total P and 93% of dissolved reactive P was removed from the simple bucket filter, while it was 95 and 99 of total P and DRP removed from the prototype. You see the performance of prototype was more robust. Even with such a low P concentration, it still worked very well. One of the prototype filter was installed for 2 drainage seasons, so we could evaluate the long-term performance of the filter in season of 17 to 18 and season of 18 to 19. 2 bars, the dark blue and light blue, represented the P concentration of inlet and outlet. Here, I only present the DRP because dissolved reactive P consists of most of the total P in the drainage water in Flanders, which is more than 90%. This is a different case from Germany and Denmark. So I only present the DRP here. The first year, 99% of P was removed, while the second year, 76%. It dropped the P removal efficiency in the second year, but it still worked very well with a larger flow in the season of 18 to 19. We will further follow up and see when the filter material will get saturated. We also checked the effect of iron co-descent particle size in the season of 18 to 19. We used iron co-descent larger than 1 millimeter and larger than 2 millimeter in the prototype filter. The filter with smaller particles showed higher P removal efficiency, up to 97%. We did see that smaller iron co-descent worked better. Perhaps it would give more reaction time. To sum up the evaluation of the filter, although it is only suitable for individual drains and mostly removed dissolved reactive P, it is very easy to install and operate with a high P removal efficiency. The cost of the filter is low because the filter material iron co-descent is a byproduct from the drinking water industry, and it causes no other contamination. The filter itself had no impact on accessibility and landscape. So we think the filter performs quite well in the drainage water in Flanders. We will further try it in with other partners to see whether it works in Denmark or Germany. Okay, that's all about my presentation. If you have any question, I will be happy to answer.
Okay, thank you, Goy. There are some questions in the chat. Let me read them out loud. So Bernd is asking, how do you explain that the observed reduction is based on dissolved reactive phosphorus reduction while it was total P in the previous presented studies? Sorry.
Sorry, can you repeat?
Yeah, so what you showed in your slides, perhaps you need to go back to the slides in which you have the results of total P and dissolved reactive P. I think Bernd is referring to the next slide in which you focused only on the, yes, on that one. So on the slide before you show that there was also, so the majority is dissolved reactive P, but of course the total P is a bit higher, so you still have total P. So why here in this case is it only dissolved P?
Oh, I explained it just easier to compare these two filters. Oh, this is
okay, from year 1 to year 2. Yeah, but you do have the total P values as well.
I do have all of the results. I just didn't present it here.
Okay, yeah, okay, yeah. Then you can exchange bilaterally with Bernd if he wants to. Another question is, have you seen any iron leaching out at the outlets?
In fact, so far we didn't do the test, but it will be interesting to follow up in the coming season.
Yeah, okay. Then how long is the retention time?
It is you mean the reaction time within the filter
how long
box?
is the water remaining in the filter actually?
Minimum 1 minute.
Minimum 1 minute, yeah. Of course, it's also depending on the flow rate. The more water is coming in, the shorter the contact time. Then Bernd is mentioning, okay, so mainly, so in Denmark, they have mainly particulate P. In Germany, the drainage water contains a lot of organic matter, and in Flanders, it's mainly dissolved P. So we have actually 3 different cases which need 3 different solutions. Then another question is, did you look into the effect of low redox?
No, it was not taken into account, but it will be interesting to look at it.
Yeah, perhaps redox values should be measured once to know where we are. Then also a second question from Stefan is, what is the effect of permeability on drainage capacity? Sorry, Stefan, the effect of permeability on...
Yeah, maybe I can say something about it.
Yeah,
in the Netherlands, we have also looked into filter systems. And in many cases, the farmers are very critical about potential blocking of the drainage by any filter systems. So was this taken into account with these filters? And do you observe any obstruction or of drainage, or could you solve this?
We actually did not, at least in last season, we did not see any clog, the drainage pipe or anything. And you see that we're dealing individual drains, the water flow is not that high. And if there is overflow, it could directly go out to the filter box without blocking the pipe.
Okay, yeah. So that's good news for the farmers then.
Yes.
Yeah, good. Thank you.
Yeah, Stefan, the overflow part is really an important part, both for the filter itself as well as for the functioning of the drainage systems of the farmers. Then Leonard also has a question. Okay, so these filters are placed in the ditch, and we know that the water level in the ditch can vary throughout the season. So can it be that the bucket is completely drowned so that it's under the water level?
Yes, it was difficult to select the right pipe to test the filter. One of the problems is in winter, some of the water level in the drains are too high, and it's even cover the outlet of the filter. Then it just means the measurement could be difficult, but I think the filter itself afterwards still work very well.
Yeah, and also Leonard, for your information, the idea is in the future, if we want to put this into practice, is to install this filter box really at the edge of the field, so not longer in the ditch, but really at the very outlet of the drainage pipe. So in that sense, if then the ditch, the water level will go up or down, normally it should not hamper the filter. But that's then...
But Charlotte?
Yeah?
If you place it at a higher level, don't you have the problem of that you have to pump the water into the bucket?
So, but it will not be a high level. So you just need to imagine where you see now on the picture that the filter is really like in the ditch. Then it will be more like, how to say, at the
bank,
at the oever, at the board, but really digged into the field a bit. So normally the water should still be able to flow into the filter. Okay, then there is another question. So the filter seems to be quite compact as we see it here on the photo. And what is the size of the filter? Like how big is it? How? It's not so big for you. It's
not so big. It's about I think the surface. I don't remember it precisely, but it's 40 times 60 and the height is 50 or 60, so it's not that large.
No, so it's half a meter high and 40 to 60, so it is indeed a compact system. Okay, does somebody else has a question? Chris, is it your hand? Do you have a question?
I don't have a question.
Okay, yeah, no problem. Okay. I don't know if there are other questions. Okay, no further questions. Then Goy, I will take over control again and go to the end of the slides. Okay, so first of all the people being present, thank you very much for listening to our project results. We will have 2 more webinars related to the NuReDrain project. So next week we will cover the results on the P recovery and the pod trials that have been done. And we will also show some results from the modeling work that has been done. And then the week after, we move on to the filter technologies that have been tested for nitrate removal. So I am aware of the fact that some people faced problems to join the meeting or to see the slides. So I hope we can solve that for the next time. So if you want to subscribe and you are not subscribed yet, then you can just go to our website and subscribe there so that you can receive the meeting link. And then with that, I would like to conclude. I want to thank all our project partners. I want to thank the Interreg North Sea Region Programme for the funding and also the much funding that we receive from the province of Antwerp, East Flanders and West Flanders here in Belgium. So take care, everybody. It was nice that you were present and yeah, let's keep in touch. Bye-bye.
Thank you. Thank you. Bye.
Bye.
Thank you. Bye.
Thank you. Goodbye.